Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 54 of the course Theory of Computation. In the previous lectures, we have seen a few NP-complete languages, right? So we first saw SAT, 3-SAT, CNF-SAT were NP-complete, which were based on Boolean formula. Then we saw that clique was NP-complete. We saw vertex cover was NP-complete. We saw Hamiltonian path was NP-complete. These were basically, we were looking for certain type of structures in graphs, right? In this lecture, we are going to see another problem that is NP-complete, which is subset sum, right? So as you will see, this problem has a different flavor when you compare with the other two types. So one was Boolean formula based and one was graph based. So this is neither. This is a different type of problem. In fact, we have already seen this problem when we introduced NP, but let's go over it again. So subset sum is the problem of given a set S and a number T, right? A set S of numbers and a target number T. The goal is to determine if the set S has a subset which sums to the target sum, right? So just for example, if the set S is this 6, 20, 32, 16 and 5, then S and 54 is in subset sum because there is a subset that sums to 54. So what is the subset? So 20, 32 gives you 52. No, that is not the one. So 32, 16 gives you 48 and then 6 gives you 54. So 32, 16 and 6 add up to 54. Then S and 42 also are a member of subset sum because there are elements or there is a subset that sums to 42. So 6, 20 and 16 add up to 42, right? However, S comma 34 is not a member of subset sum because there is no subset that adds up to 34, right? So the question is there a subset that adds up to the given value, right? There is no subset that adds up to 1, right? So the question is, given a subset and a target sum, given a set S and a target sum, is there a subset of S that sums to the target sum, right? So as you see, it's a completely different type of problem. There is no graphs involved, there is no Boolean formula involved. All that you have is a set S and a number T. Is there a subset of the set S that adds up to the number T, right? And this problem is NP-complete, right? And by following the approach that we used in the previous lectures, we need to do two things. One is to show that this is an NP, and second is to show that a known NP-complete language reduces to subset sum. So showing that it is an NP is something that we have already done in lecture 46, right? So we do the standard guess and verify thing. We not deterministically select a subset of S, right? By picking or not picking each element. So S has, let's say, k elements. So we pick or not pick each element, and then we get a subset of S. And then we, once we get the subset, we just verify whether the selected subset adds up to T, right? So this is also straightforward. So there is a non deterministic guessing followed by a verification, right? And if the selected subset adds up to T, we accept, else we reject, right? So if there is a subset, this will accept, and if there is no subset, it will reject, right? So this is a valid non-deterministic algorithm, and it also runs in polynomial time. Hence, subset sum is an NP, right? So now let us focus on the main part, as always, to show that it is show that an NP-complete language reduces to subset sum, right? So we show that 3-SAT reduces to subset sum, right? So like many other cases before, we show that 3-SAT reduces to subset sum. So what do we have to do? Given a Boolean formula or given a 3CNF formula phi, we have to construct a set S and a number T such that phi is satisfiable if and only if S contains a subset of size of some T, right? Phi is in 3-SAT if and only if ST is a yes instance of subset sum, right? So let phi be a formula with n variables, okay, so this is just some assumption, and m clauses, right. So it's a 3CNF formula, meaning it is an AND of m clauses, where each clause is an OR of 3 literals, right, and overall there are n variables. And let's say the let's just go one step further, and let's say that the n variables are x1, x2, x1, x2, xn. Let these be the n variables, okay. And so we have an AND of clauses where each clause is an OR of 3 literals, right. So the literals could be of the form xi or xi complement, right. Now we will say how to construct the subset sum instance, right. So it should have the property that, so we should produce a set S and a number T such that if I is satisfiable, the set should have a subset that sums to T. If I is not satisfiable, the set should not have any subset that sums to T, right. So we construct S with 2 times n plus m numbers, right. So where n is the number of clauses in the SAT instance, and n is the number of variables and m is the number of clauses, right. 2 times n plus m, right. So the way we build the instance is like this, right. So look at this table that we have, and what we will do is what we are going to do is to each row, so this table has 2 times m plus n rows, and each row corresponds to one number in the set, right. So each entry is like a 0 or 1. We have to read the entries from left to right to get the number that this row corresponds to, right. So it's just, you just read it as a single number. In fact, you are even though it is only consisting of 0 and 1, we are going to be reading it as a decimal number, not a binary number, okay. So this is very important. We are going to be interpreting these numbers as decimal numbers. So there are decimal numbers that consist of only the digits 0 and 1. So these are going to be the numbers that we have in the instance, okay. So let's see how to build this table, and then I will again say how to interpret this, right. So this has n plus m columns. So the first n columns are indexed by 1 to n. Right. The next m columns are indexed with the clauses C1 to Cm. Right. These m columns. So we have n columns followed by m columns, and the rows are actually there are 2n plus 2m rows, and each of these corresponds to a number, right. So the first row is indexed y1, or it's labeled y1. Second row is labeled z1. Then we have y2 and z2. Then we have y3 and z3, and so on till yn zn. So that marks this boundary. Then we have, so this is 2n numbers, y1 z1, y2 z2, y3 z3, and so on up to yn zn. Then we have g1 h1, g2 h2, and so on up to gm hm. So we have 2n rows followed by 2m rows, right. And for convenience, we will divide this table like this, or divide this matrix like this, and that will help us easily figure out what are the entries, right. So constructing the set is going to be like finding the numbers, but the numbers are just reading this table or matrix from left to right. So we will be filling up this table, right. So the numbers in the set are going to be y1 z1, y2 z2, y3 z3 up to yn zn. Then g1 h1, g2 h2, g3 h3 up to gm hm. So these are going to be the 2m plus 2n numbers, right. And each number is like, we read this number from left to right. Like, so y1 is, we just read this thing, read the first row from left to right. So y1 is 1 0 0 0 0 0 up to n, up to the nth place, then followed by again 1 0 0 0. So I'll explain now how to fill the entries. So first let us focus on this this quadrant of the table, this part which has the first 2n rows and the first n columns, right? So it's very simple. Y1, Z1 start with 1 and then all zeros. Z1 also is the same. So in fact, Y and Z are going to be identical. Y1, Z1 is going to be identical in this part, and Y2, Z2 are also going to be identical, and Y3, Z3, everything is going to be identical this part. This is where they will differ. So in this part, Y1 and Z1 have a 1 under 1 and rest zeros. Y2, Z2 have a 1 under 2 and the rest zeros. Y3 and Z3 have a 1 under 3 and the rest zeros, right? And so on until Yn and Zn, they have all like so these I could also have filled zeros here, because like a leading zero does not change the number, right? So 0 followed by 1, 0, 1, 0, 0 is the same as 100, right? So I can fill leading zeros here, but I am not filling it. So Y and Zn is just all zeros and a 1 at the end position, right? So this is how we fill this part. Now let us see how we fill this part, right? So what we do here is we look at, so each of these columns, right? So corresponding to this part, so the rows correspond to Y1, Z1, Y2, Z2 and so on. The columns correspond to each of the clauses, C1, C2 up to Cm. There are m clauses. So what we do is, so Y, let's say the entry between Y1 and C1. So Y1 corresponds to X1, okay. So if X1 appears in the clause C1, then we have this entry 1, okay. And let's say Y2 and C3 there is a 1. This means X2 appears in the clause C3. And also Y2 and Cm there is a 1. This means X2 appears in the clause Cm. Okay, what is Z? Z2 and C2 there is a 1. So Z2 also corresponds to X2, but the negated form of X2. So this indicates that X2 complement appears in clause 2, right? So I have written this again below. If Xi is in the clause J, we put a 1 against Yi and Cj. If Xi complement is in the clause J, we put a 1 against Zi and Cj, right? And everything else is 0. So I am just referring to this part, everything else is 0. So this indicates that X1 appears in C1. This indicates that X2 appears in C3, right? Because it is Y2 and C3. This indicates that X2 complement appears in C2, right? So that's how we fill up this. Now each variable may appear in multiple clauses, there is no limit. So there could be many ones in this part, but each clause we know contains only three literals. So if you look at this part, if you look under any clause, this part, we will find exactly 3 ones, because every clause contains 3 literals. So this part will contain 3 ones, no more than 3 ones, right? Because let's say let's say C3 contains X2, X5 and X6, right? So the Y2, Y5 and Y6 will be 1, right? Or X2, X5 complement, X6 complement. So then Y2, Z5 and Z6 will be 1, right? So whichever is the 3 literals, the rows corresponding to that will be 1 under each clause. So once again, here each row may have multiple ones, there is no limit, but each column will have exactly 3 ones. When I say here, I am just talking about inside this box, top right box, right? So this is the part that is slightly, this is the part that only, this is the only part that depends on the formula, Boolean formula, right? The other part depend on the Boolean formula only for the number of variables, but this is the part that actually looks at the formula and decides something. The rest is just very straightforward. The bottom left part, this part is very easy. The entire part is 0. Okay, so there is nothing to, like, you can entirely fill zeros, but this is also a leading, it is also leading this number, so you can also imagine it's nothing, right? So now let us come to the bottom right part. This is similar to the top right part. So against G1, so the rows are indexed G1, H1, G2, H2, G3, H3 and GM, HM, right? And the columns are C1 up to Cm. So there are 2m rows and m columns. So the first two rows have a 1 in the under C1. So G1 and H1 have a 1 under C1 and zeros following that. G2 and H2 have a 1 under C2 and zeros following that. G3 and H3 have a 1 under C3 and zeros following. And so on until GM and HM have only two ones under, GM and HM have ones only under CM. So that completes this. Right. So once again, the top left is Y1 and Z1 have 1 under 1, Y2 and Z2 have 1 under 2, Y3 and Z3 have 1 under 3 and Yn and Zn have 1 under n. The rest are zeros. Then bottom right, G1 and H1 have 1 under C1, G2 and H2 have 1 under C2, G3 and H3 have 1 under C3 and so on up to GM and HM have 1 under Cm and the rest are all zeros. This bottom left is entirely 0, right? And finally the top right, if xi appears in the clause J, right, we put a 1 against yi and cj. If xi complement appears in clause J, we put a 1 against zi and cj. So here this indicates that x2 appears in C3, this indicates that x2 complement appears in C2. Okay, so that is how we build this. So now we can read the entries like this. So y1 is the number 100000 and then 10000. Y2 for instance is 010000 and 001 something and 1, right? For instance, GM and HM is simply 1 because all of this is leading zeros and at the end is 1. So GM is 1, HM is 1, G1 is 1 followed by m minus 1 zeros, H1 is 1 followed by m minus 1 zeros. And once again I am reiterating, all numbers are in decimal, okay? All numbers in decimal. Okay, so this is not binary, it is decimal, right? So there is a reason for it. And finally, so this gives you the set S. So I have completely described what are the 2m plus 2n numbers, right? So the listing of these numbers gives a set S. What is T? T is simply this number, the number that is listed here. Maybe I'll just color it differently. It is a number with 1 1 1 1 1 1. So there are n ones followed by m3s. Okay, so I am just aligned it with the table so that it's clear. So it's n ones followed by m3s. So obviously there is no confusion with T because it is certainly not binary because we have 3s as a digit, right? So T is also in decimal. Everything is in decimal here, right? Even though the elements of S have digits 0 and 1, it's to be read in decimal, right? So we have completed the construction. I have completely described it. Once again, all the numbers are to be read as decimal numbers, right? So S I have described, and the construction is clearly in polynomial time because construction mainly involves building this table, and this table has 2 times m plus n rows and m plus n columns. So 2 times m plus n whole squared number of entries, which is polynomial in the size of the formula given, right? So the construction is polynomial time. So what remains to show is the correspondence. The formula is satisfiable if and only if the set has a subset that sums to T, right? So T also we have defined. T is this number with n ones followed by m threes, right? So we need to show this correspondence. As usual, we will show it both directions. First we will show the forward direction, We assume that the formula is satisfiable and then show that there is a subset that sums to T, right? So the formula is satisfiable, which means there is a way to assign true false to the variables xi, right? Such that each clause is satisfied, right? So now how do we pick the subset of S, right? So from S we need to pick a subset, right? So S is these numbers, each row corresponds to a number, and we need to get this sum, the sum that is over here, right? So how are we going to pick? So notice that we have the first n positions are all 1 in T. So where do we get these ones from? So these ones have to come from here, from the top left, because the bottom left are all zeros. So what we will do is for each variable I, we have to pick yi or zi. We cannot pick both because then the sum will change. So we will pick only one of yi or zi, exactly one of yi or zi for each one. So how are we going to pick it? So let me tell it right away. If x, so the assumption is that the formula is satisfiable. So there is a satisfying assignment. So if the satisfying assignment sets x1 to true, we pick y1 and not z1. If the satisfying assignment picks x1 to be false, we pick z1 and not y1. Similarly for y2, z2 and so on. If x2 is true in the satisfying assignment, we pick y2 and not z2. If x2 is false in the satisfying assignment, we pick z2 and not y2, right? And that is the rule of picking which elements in. So that will tell us how to pick y1, z1. So for each I, we pick exactly one of yi or zi, right? So that will take care of this part of T. Now we have to handle this part of T, the trailing threes. How are we going to get this sum? So we have told how to pick n numbers from y1, z1, y2, z2 and so on. So now we will say how to pick the remaining numbers from g1, h1, g2, h2 and so on, right? So notice that each clause has a satisfying assignment, right? So consider clause 1, right? Each clause has a satisfying assignment, meaning each clause has a true literal. So clause 1 contains one true literal. Suppose x1 is the true literal in the clause, and then that means x1 is set to true, right? So that means since we picked y1, so if x1 is set to true, we would have picked y1, right, and not z1. And since x1 appears in the clause as it is, there will be one that is contributed to by y1, right? So if x1 is set to true, and if clause 1 is satisfied because of x1, then we get a 1 from the y1 under that column. Suppose x2 complement, so x2 complement is there in C2. Suppose this makes the clause satisfied, which means x2 is set to false in the satisfying assignment, right? Only then x2 complement can satisfy the clause 2, which means we pick the row z2. So which means this one is already there under C2. So the point is that just by the choice of y1, z1, y2, z2 and so on, under each clause we already have at least one already. So under C1, because it's a satisfying assignment, under C1 there will be one that is contributed from this part. Under C2 there will be one, at least one, right? So if the clause has only one true literal, it will have only one. If it maybe the satisfying assignment can have more than one true literal, right? So then it will have more than one, right? So it could have all three could be true, right? So each clause will have at least one under it from the top right part, and it will have at most 3 ones because each clause can have at most 3 literals. So under under each clause, the contribution from the y's and z's will be at least 1 1 and at most 3 ones, right? But then t, the sum t, the part corresponding to the sum here, this target sum here, is all 3's, right? So what if for a certain clause there is only one true literal, one satisfying one true literal, which means there is only one 1 here, which means we need to get 2 more ones to get this sum 3. So no problem, we have G1 that will contribute another 1 and H1 that will contribute another 1, right? So we can add G1 and H1. Suppose in clause 2 there are two true literals, right? Let's say x2 complement and x3, right? But not the third literal is not true. So but then the target needs to be 3, right? So we just include G2 in the subset, but we do not include H2. So by including G2 we will make the sum 3. Suppose some other clause, let's say CM, that already has 3 true literals, which means it will already have 3 ones from the y's and z's, which means we will not include either GM or HM, right? So depending on how many ones are contributed to in each clause by the chosen y's and z's, so it could be 1, 2 or 3. If it is 1, we have to include both the corresponding G and H. If it is 2, then we have to include G but not H. If it is all 3, then we will exclude both G and H, right? So that way we will include or exclude each G and H in order to in such a way that we will get the target sum to be exactly 3. So now under each clause we will ensure that the sum is 3, and by the choice of y and z we have already ensured that the sum of this part is 1. And because we are seeing it as decimal, right, it is not at all messy, there is no carry or anything, because the sum is going to be just 3 here, so there is no question of any carry bit or carry digit coming, right? And here also it's completely fine. So there is no interdependence between the digits. So that shows that when the formula is satisfiable, the set S has a subset that sums to target, right? So this is how we choose x and y or z, right? If xi is true, we pick yi and not zi. If xi is false, we pick zi and not yi. And because of what I said, under each column it has at least one from the first 2n rows, right? 2n rows. This is 2n rows, not zn rows, and at most 3 ones. And then we decide to include gj or both gj and hj, or exclude gj and hj to make the sum under the cj's to 3. So this shows that the set st or the set S has a subset that sums to t, right? So this completes one direction of the proof. If phi is satisfiable, then there is a subset that sums to t. Now the other direction. Suppose there is a subset that sums to t, right? So now let us see what is happening. We know that, so let's try to understand some properties. So if you look at each column here, let's say the leading columns, the leading n columns, there are only 2 ones in each such column, because the bottom part is all zeros, the top part contributes 2 ones exactly. If you look at the last m columns, the top part corresponds to the literals of a clause. So this contributes to exactly 3 literals. So this contributes exactly 3 ones, and the bottom part gives 2 ones. So the number of ones here in each of these columns is going to be 5, right? So the point is that since even if you include all the y's and z's and the g's and h's, right, even then the sum of each column here is going to be no more than 5. So the second these m columns, the sum is going to be no more than 5. The first n columns, actually the sum is going to be no more than 2. So even in the worst case of including all these numbers, the sum is going to be, sum of each column is not going to be more than 5, which means there will be no carry ever in the addition here. This is true even if all the numbers are picked. So this will certainly be true even if a subset is picked. So this is very convenient. So this makes the thing clean, because it is not like this column can force something happen in the next column or whatever. Everything is separate and can be seen separate, right? So there is no carry, right? And this will be useful, right? So all the digits are 0, 1, so that's also useful, and this is why we want to go to the decimal system, because we have up to 10, so this allows us to not carry, right? Right. So now there is a subset that sums to this sum. We already have told that there is no, we have already established that there is no carry. So which means from the first 2n rows, y's and z's, we can only have one of each of them. So from y1 and z1 we could only have one, because if we pick both y1 and z1, we will not get this one in the target. And if you don't pick either of them, then we will have 0 here. So we need to have exactly one of y1 and z1, exactly one of y2 and z2, and so on. And this gives us the assignment. So so the assumption is that the set S has a subset that sums to T. From the subset we are going to build a satisfying assignment. What I just said is that for each I, either yi is there or zi is there, but not both. So if yi is there in the subset, we make that corresponding xi to be true. If zi is there in the subset, we make that xi to be false. This is how we are going to set the variables, right? So if yi is in the subset, right, set xi to true. If zi is there in the subset, we set xi to false. And as it is, we have already established that it's exactly one of yi or zi that is going to be there in the subset, right? Now we have to, so we have an assignment. Now we have to show that this is satisfying, right? Why is it satisfying? So we have a subset that sums to T, right? We know from each of the first 2n rows, we have picked exactly one of yi or zi, right? Right, and we know that from we know that the last, let's say the clause columns, these columns for instance, the sum is 3, right, because there is no carry, and we know that this part can contribute at most 2, right, because there is at most 2, like G and H will contribute 1 each, that, and the contribution that can come from this part is at most 2 for each clause, which means each clause has at least one coming from the top part. The C1 has at least one coming from the top part. So suppose it is coming from some yi, right, which means that xi was set to true, and if there is a 1 under C1 and yi, this means that xi is appearing in the positive form in the clause C1. And by the way we set the variable in the assignment, xi was set to true, and that is going to satisfy the clause. Suppose the one from here is going to come from some zi. This means xi complement appears in the clause, right? And since zi is contributing to this part, we know that the variable xi would have been set to false, right? That's how we picked the value of, that's how we set the value of xi. Since zi is in the subset, we've set xi to false, right? So once again, the point is that first for each of these, so we have a subset that sums to T, right, and we establish there is no carry. So to get the leading digits all 1, we for each I we pick exactly, or for each I exactly one of yi or zi is there in the subset, right? Both of them cannot be there, none of them also cannot be there, exactly one has to be there. If yi is there, we pick xi to be true. If zi is there, we set xi to be false, right? And now we look at the second part, second set of columns, the clause columns. These parts, the bottom part can contribute at most 2, right? But then the target sum has 3 in those parts, which means there should be some contribution from the subset from the top part. If the contribution comes from yi, that is because the variable xi appears in the clause, and if the contribution comes from yi, it means that xi should be set to true in the satisfying assignment, right? Because we have yi in the subset, right? Why is yi in the subset? Okay, yi is there in the subset, which means xi would have been set to true. If the contribution from the top part of the clause comes from some zi, we know that xi complement is there in the clause, right? Otherwise that entry will not be 1. And further, since zi was part of the subset, right? Otherwise it will not be contributing. We know that xi would have been set to false. So even in that case also the clause is set to the clause. There is one literal in the clause that is satisfying the clause. So in either case the clause is satisfied. So in the last m columns we need the sum to be 3 each, and the contribution from the bottom part is at most 2. So for each Cj there must be contribution of at least 1 from yi or zi. If the contribution is from yi, then xi appears in the clause and it is set to true. If the contribution is from zi, then xi complement appears in that clause and xi is set to false, which means xi complement is true and hence satisfies that clause. So in whichever case the clause is satisfied, right? So whichever case the clause is satisfied, and that shows that if the set has a subset that sums to T, the formula is satisfied or satisfiable. That is a satisfying assignment, and that completes the proof of the correspondence that phi is satisfiable if and only if S has a subset that sums to T, right? And that completes the proof of the NP completeness of subset sum. So there you go, you have yet another problem which is just talking about sets of numbers and some subset achieving a target sum. It's entirely different from graphs and having cliques or independent sets or Boolean formulas. It's a different type of problem, but that also is NP complete, right? So just to summarize, to show that it is an NP was easy, right? A standard guess and verify approach. To show that it is NP complete, we have to reduce it from 3 sat. So given a 3 sat instance, we build these numbers which are whose digits are entirely 0, 1, but we view them as decimal numbers. 2m plus 2n numbers, where m is the number of clauses in the formula and n is the number of variables, and the target sum is 1 1 1 1 1 n 1s followed by m 3s, right? And then we showed that if the formula is satisfiable, there exists a subset, and if that sums to the target, and if there is a subset that sums to the target, the formula is satisfiable, right? And obviously the construction of this is in polynomial time, because the number of entries is polynomial in the size of the formula, and that completes the proof. So, and that completes the lecture number 54, and I'll see you in the next lecture where we will see yet another NP complete problem. Thank you.